Assalamualaikum and hi everyone. We see again in the second subtopic under topic thermochemistry, that is 2.2 calorimetry. Okay, here is what you are going to learn under topic 2.2 calorimetry. So first define what is heat capacity. Specific heat capacity, calculate the heat change in a constant pressure calorimetry, simple calorimeter, and constant volume calorimetry, bomb calorimeter. Have you ever read the food label of your prosperity burger and seen how many calories your burger contains? Ever wondered how they know this? The technique used is calorimetry. This is the science of measuring heat transfer when a substance absorbs or gives out heat. Calorimetry is a method used in the laboratory to measure the heat change of a reaction. So the apparatus used is known as calorimeter. So there are two types of calorimeter, that is simple calorimeter and bomb calorimeter. A simple calorimeter is a constant pressure calorimeter typically used for solution-based chemistry and as such generally involve a reaction with little or no volume changes. For example, if we were trying to determine the heat of fusion of ice melting inside a coffee cup calorimeter, we know that heat is only exchanged between ice and water. So therefore, we can assume that the energy gained by ice while melting is equal in magnitude but opposite in sign to the energy lost by the water inside the calorimeter. Okay, another name for the simple calorimeter is also known as coffee cup calorimeter, which consists of styrofoam cups that reacts as an insulator for the reaction mixture from the surrounding. So we can assume that there is no heat loss to the surrounding. And then we have a thermometer and a stirrer. So therefore, heat released by the reaction is absorbed by the solution and the calorimeter. A bomb calorimeter is used to measure the heat that a reaction absorbs or releases and is practically used to measure the calorie content of food. A bomb calorimeter is a type of constant volume calorimeter used to measure a particular reaction's heat of combustion. For instance, if we were interested in determining the heat content of a sushi roll, for example, we would be looking to find out number of calories it contains. In order to do this, we would place the sushi roll in a steel bomb, seal it, and then immerse it in the water inside the calorimeter. Then we would evacuate all the air out of the bomb before pumping in pure oxygen gas. After the oxygen is added, an electrical source would ignite the sample, causing it to combust, thereby yielding carbon dioxide, water vapor, and heat. As such, bomb calorimeters are built to withstand the large pressures produced from the gaseous products in these combustion reactions. Once the sample is completely combusted, the heat released in the reaction transfers to the water and the calorimeter. The temperature change of the water is measured with a thermometer. The total heat given off in the reaction will be equal to the heat gained by the water and the calorimeter. There are two important terms in calorimeter: specific heat capacity, so the symbol is small c, and heat capacity capital C. So what is the differences here is specific heat capacity is the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. Whereas for the heat capacity, capital C is the amount of heat required to raise the temperature of a given quantity of the substance by 1 degree Celsius. So the difference here is specific heat capacity is involve 1 gram of the substance, whereas for the heat capacity, a given quantity of the substance. Unit for the specific heat capacity is joule per gram per degree of Celsius, whereas for the unit for heat capacity is joule per Celsius. So here is the very basic principle in calorimeter. So as the heat released by a reaction, so the heat will be absorbed by the surrounding. So surrounding here could be three types of surroundings that are calorimeter itself. So therefore we will get this formula. Q reaction is equals to C delta T, where C here is referred to the heat capacity of calorimeter. Delta T is referred to the temperature change. If the surrounding is water and calorimeter, so the formula would become Q reaction is equals to MW CW delta T plus CC delta T, where MW here is referred to the mass of water, CW is referred to the specific heat capacity for water, okay, and delta T, temperature change, CC is referred to heat capacity for calorimeter. Alright, so for the surrounding that involve water itself, so we will get this formula. Q reaction is equals to MW CW delta T, where MW is referred to mass of water, CW or specific heat capacity of water, and delta T is referred to the temperature change. So please remember, so if the surrounding is only calorimeter, so you will get this formula. So Q reaction is equals to CAT. Okay, if water and also calorimeter, you will get this formula. Q reaction MCAT plus CAT, and water, only water, so Q reaction is equals to MCAT. Okay, for the first example, in an experiment, 0.1 gram of hydrogen gas and excess of oxygen gas were compressed into a 1 liter bomb and placed into a calorimeter with heat capacity of 9.08 times 10 power 4 joule per degree of Celsius. The initial temperature of the calorimeter was 25 degrees of Celsius, and finally it increased to 25.155 degrees of Celsius. Calculate the amount of heat release in the reaction to form H2O, and then you have to express it in kilojoule per mole. So first of all, you have to find out all the information from the question. So first is about the delta T. So how that we can calculate delta T? We have initial temperature 25, final temperature is 25.155. So find out the value of delta T. Okay, and then also given to you is already mentioned bomb. The word here is bomb, calorimeter. So therefore, we have given also the calorimeter with heat capacity. Okay, this is the value. And then the mass of hydrogen gas 0.1. Okay, and then we have to find out the heat release in the reaction to form H2O. Alright, so what should we do? So here is how you can solve this problem. So heat released by X mole H2 gas is equals to heat absorbed by calorimeter. Why only the calorimeter? So because in the question here, it's not giving to you the mass of water. Okay. So and then it's referred here bomb calorimeter and no mass of water. So this statement you have to include in your calculation. So this is the first mark given to you. And then write the formula involved. Q reaction is equals to CC delta T. So why we use this formula? Because in the question does not given to you the mass of water and there is no mass of calorimeter. Alright, so next substitute all the values here. Okay. And finally we'll get the value of heat release is 14074 joule, convert it into kilojoule. Okay. Alright, next write the equation involved. So we want to find out formation of H2O. So H2O liquid should be 1 mole. So therefore, you have to balance at the right hand side. So become like this. Right. So in the question, it's already given the mass of hydrogen gas. So from here, you can find out the mole of hydrogen gas. Okay. So mass over water mass. Mole of hydrogen gas is 0.05 mole. So we want to calculate what is the number of mole of water formed. Okay, So since from the equation here, 1 mole of hydrogen gas is equivalent to 1 mole of H2O formed. So therefore, number of mole of H2O is equivalent to the number of mole of hydrogen gas. Alright, so next, by using stoichiometric method, okay, so you can find out the heat release. So 0.05 mole of H2O, so actually it will produce 14.074 kilojoule energy. So from the equation here, we want to find out the mole for 1 mole of H2O form. So if 1 mole of H2O release, how many energy? So therefore you get 281.48 kilojoule. And then because we use stoichiometric method and we get the value of heat release become positive, therefore write your conclusion again like this. Okay, heat of reaction delta H naught is equals to negative 281.48 kilojoule per mole. Okay, so we move to the second example. Calculate the amount of heat released in a reaction in an aluminium calorimeter with a mass of 3087 gram and contain 1700 ml of water. The initial temperature of the calorimeter is 25 degrees Celsius and it is increased to 27.8 degrees Celsius, and given to you also the specific heat capacity of aluminium, okay, and specific heat capacity of water. Alright, so water density, so 1 gram per ml. Right, so these are the information that we get from the question. So first we can calculate the value of delta T. T initial 25, T final 27.8. So T final minus T initial. Therefore, you get the value of delta T. Alright, and then from here is already given two information about the calorimeter, that is specific heat capacity and also the mass of calorimeter. It's already given to you the volume of water and specific heat capacity of water. Okay, and we want to calculate the heat release from the reaction. Okay, so based on the data given in the question, you can write the statement. So statement 1 mark. Okay, heat released by reaction is equals to heat absorbed by aluminium calorimeter plus heat absorbed by water. How that we can get this statement? Because in the question have the information about the calorimeter as well as information about water. So the formula that we are going to use is Q equals to MWCW delta T plus MCCC delta T. So MW is referred to the mass of water. It is not directly given in the question. However, you can calculate from the water density 1 gram per ml and the volume of water 1700 ml. So from here you can convert it into mass and then substitute all the values. Okay, delta T here, T final 27.8 minus 25, you get delta T final. Okay, finally, when you substitute, then you get heat of reaction is 25 kilojoule. Always remember, you have to write the conclusion. Okay, because from here, we'll get the value here is positive value, right? So, and the question asks about amount of heat release. So, it should be negative value. So, therefore, you have to write the heat of reaction is equals to negative 25 kilojoule. Okay, so for this one, no need to write per mole since we don't know what type of enthalpy involved here. Okay, now we move to example number 3. The heat of neutralization for the following reaction is negative 56.2 kJ per mole. So the reaction of neutralization involves sodium hydroxide. We add with HCl, produce NaCl and water. So 100 ml of 1.5 molar HCl is mixed with 100 ml of 1.5 molar NaOH in a calorimeter having a heat capacity of 15.2 joule per degree of Celsius. The initial temperature of HCl and NaOH solution are 23.2 degree of Celsius. Calculate the final temperature for this reaction. Given to you the density of solution 1 gram per ml and also specific heat capacity of the solution is 4.18 joule per gram per degree of Celsius. Because it involves neutralization, so usually we will use simple calorimeter. Our target is we want to calculate the final temperature, T final. T initial is already given. Right, and then also given the heat capacity of calorimeter and then also the volume and the concentration of the acid and base, density solution, and specific heat capacity of the solution. Okay, so what should we do first? Alright, so the first step, you can calculate the number of mole of water in this reaction. So by using molarity of acid and its volume. Okay, so you can choose either HCl or NaOH because it is equivalent. Let's say we want to calculate mole of NaOH. Therefore, mole of NaOH is equivalent to mole of HCl and is equivalent to the mole of H2O. So molarity time with the volume, so we get 0.15 mole. So this is the amount of water formed during the reaction, during the neutralization reaction. In the question, it's already given the heat of neutralization, negative 56.2 kJ per mole, which means 1 mole of water formed, it will release 56.2 kJ of heat. However, we only use 0.5 mole water form. So therefore, you can use stoichiometric method to find out how many heat released for 0.15 mole of water. Okay, and then you will get here negative 8.43 kilojoule of heat release. Okay, based on the data given, we will get this statement. So heat released by reaction is equal to heat absorbed by calorimeter plus heat absorbed by solution. So, because in the question given to you information about the solution or the mixture, okay, and calorimeter, heat capacity of calorimeter. So, therefore, the formula that we use here, so Cc here is referred to the heat capacity of calorimeter, 15.2. Ms is referred to the mass of solution form. So meaning that we have combined the solution form 100 ml plus 100 ml, then we get 200 ml volume. From the data, it's already given the density of solution, then you can convert from ml, 100 ml to mass. Okay, and then Cs is already given, specific heat capacity of solution 4.18. Okay, delta T is what we want to find out. The value of Q we already calculate, that is 8.43 kilojoule. Okay, now substitute. Okay, remember you have to convert from unit kilojoule into joule. Just substitute the value only without the sign. The sign here is to show heat release. Okay, so why that the Q should be in joule? So this is because the unit of heat capacity is in joule. The unit of specific heat capacity of solution also in joule. So we want, okay, and then substitute all the values. Mass of solution is 200 gram, and therefore the value of delta T is 9.904 degree of Celsius. We know that delta T here is referred to the T final minus T initial. Okay, and therefore the value of final temperature is T initial plus delta T. Okay, and final temperature is 33.1 degree of. Okay, so now we move to the example number 4. A calorimeter contains 400 ml of water at 25 degree of Celsius. If 600 ml of water at 60 degree of Celsius is added to it, determine the final temperature. Assume that the heat absorbed by calorimeter is negligible. So meaning that calorimeter is not involved in the calculation. So we take a look at the data given. So we have 600 ml water, which refer to the hot water at 60 degree of Celsius, is added to 400 ml water at 25 degree, and then we want to find out the final temperature after the water have mixed. Okay, first you have to write down the statement. So heat released by added hot water. So hot water, it will release heat. And whereas for the cold water or normal water, it will absorb the heat released by the hot water. So therefore, we will get this formula. MC delta T1 equal to MC delta T2. M here is referred to the mass of hot water. C here is the specific heat capacity of water that is already included in the list of selected constant values. So you can refer to that. M here is referred to the mass of cold water, 400. Okay, and C here is the specific heat capacity of water. So, but first we have to define what is delta T1 and delta T2. Okay, delta T1 is referred to the heat change in hot water. The initial temperature of hot water is 60. Okay, when it is transferred into normal water, of course, its temperature will drop. So, that's why 60 degree of Celsius minus Y. Okay, as for the delta T2, that is referred to the changes in cold water or normal water here. The initial temperature is 25 and temperature of the cold water, it will increase. Final temperature, that is Y minus 25 the initial temperature. Okay, you can substitute. Okay, make sure convert from ml into gram. So because we know that density of water is equals to 1 gram per ml. Substitute in the formula and you will get value of y is equals to 46 degree of Celsius.